be unique. There may be one word very close to another word. This can be like semantically very close to each other. So vector wise, their vectors should also be very close to each other. So that is the possibility. But every words must have individual representation. So that's what also Oxford says. So, according to, if we think of vector space model, if we represent a word in a vector with some n dimension, so that will be the more appropriate representation of words. So now finding out those dimensions and the values of those dimensions for particular word is main objective to fulfill in order to find a better model for word representation. So in a graphical way, we can understand more better way here. So we know that sentence is nothing but a sequence of words. So if we consider those words as a dimension, like here, term one, term two, same voice, term n. So because the dimensions are very large, so suppose think of three-dimension space. If we plot various sentences on that, so the sentences which are close to each other, their vector will also be very very close when we represent in terms of those words. So what it says that, so there is our similarity in the terms which are there in those two sentences. If two sentences are very opposite to each other, their vector representation will also be very very different in a very different direction. So that's how the vector space model give us also a graphical understanding how the sentence, the piece of text would be represented in an n dimension space. So we'll see various approaches of word representation. So firstly, as we decided that we'll talk about some non-semantic word representation. They are initially devised and used as a rule-based method. And then we'll see the semantic word representation. What is the need of that? And in non-semantic word representation, why we are calling non-semantic here is because uh, they don't carry any neighboring or any context information. Each individual word will have a unique vector and without any considering any contextual or any kind of neighboring information which will be there in surrounding situation in a particular sentence or document. So that's this is the first type of word representation that people try, and they are helpful for some very basic applications, but most of the applications they're not. But to understand the main agenda of word representation, it helps a lot in understanding how a word can be represented as a one hot vector. So how this one hot vector representation is defined for each and every word. So first of all, for a given set of sentences, we will find out the unique words. We'll assign a unique ID to each and word individually in the corpus. And then based on that unique ID, we'll assign one hot vector to each of the words. So we'll, no, don't worry, we'll also see some coding examples to understand how this will be implemented. So yeah, with this example, it will be more understandable how one hot vector is designed for a given sentence. So suppose sentence is RMS Titanic was a British passenger liner. So it is some sentence which consists of some words. If you count them, 1, 2, 3, 4, 5, 6, 7. So there are 7 words, and they all are unique. So we can assign unique ID to them. Suppose RMS is got one ID, Titanic 2, 3, 4, 5, 6. So each word got a unique ID. And now based on that unique ID, we simply create a one hot vector. Like RMS, the unique ID is 1. So at one place it will be 1, the rest of the places it will be 0. So this vector representation is a one hot representation for this first word, which is RMS. For the Titanic, because we have assigned the ID 2, at the second place we'll place 1 and rest will be 0. So that's how we can represent the one hot vector for each and every word in a given corpus. Yeah, so there is a small example to understand how it could be done by using Keras library. TensorFlow library, Torch library also had the same function, so you can just follow the same idea and implement it other places as well. So just let me quickly. We cannot connect multiple sessions together, so yeah, yeah, it's ready. So we will be using this the Keras, the TensorFlow Keras library, and two categorical method, which actually help us generating one hot vector for each word. Taking the example like this sentence a bit longer than the example that we have seen recently. RMS Titanic was a British passenger liner that sank in the North Atlantic Ocean, something something. So to first we need to find out the unique words. So as we discussed yesterday, we can simply use the split function on this text. Split will divide, or we can say extract all the words in this sentence in a sequential manner, and then we can find out those words as well as find out the list of those words. So let's execute and see the output. Yeah. So this is how. So after splitting this string, we got these many sequence of words: RMS, Titanic, was a British passenger liner, something like that. And then what we'll have to do is create indexing. Indexing is nothing but finding out the ID of a particular word. So we will create a dictionary where the key would be word, and the number associated or ID associated with that word will be the value in that dictionary. So we are generating this index simply by this loop. In this loop, it is taking that the list of words, and we are also calling set function. The set function, we know that in the Python what it does is it removes all the duplicate words. So after this applying the set function, or converting this list into set, will automatically remove the duplicate words, and then again will transform into list, and then enumerate. We know that enumerate returns two things: one is the index and one is the actual value. So I is the position of that word, which is, so suppose RMS is the first word, so for that I value will be 0. So likewise, the index will be created. So let's execute it. Yeah, indexing is done. Now let's print the indexing. Yeah. So because we know that the set is unordered list, so it creates unordered sequence of elements. So that's why you must observe that uh, the word sequence that we observe here is different here. Okay, because of the set, but ultimately it assigns the unique ID to each and every word, and also removing the duplicity. So the total number of unique words that we observe is 29. And now after getting the index, next thing is to just generating the one hot vector. So, and it is also called as one hot encoding. Sometimes both are the same thing. So assigning word index to each word. So this is reverse of the above order. So this is word to ID, and this is uh, no, here we are just assigning the unique ID for each word. here. Just getting the index of each word which are there in this sentence. So the first word is RMS. So for the RMS, the its index is 22. The second is Titanic. Titanic got 0 index. So it's just printing the index in the same sequence which are there in the given sentence. Now it will take this list as an input to this categorical function, and it will generate the one hot vector for each word in this list. Okay, so if we just directly execute and see okay, we need to execute it. Yeah, now yes. So we observe that we can see all the words in this sentence. Now we got the one hot vector for each. So this one hot vector is for the sorry. So this one hot vector which has the ID 22. So you must can calculate and see that this is some 21 or 22 location. The one is there, and similarly the one hot vector for each word we observe. So this is how this sentence is represented using one hot vector. So for each vector, we observe that there is only one place where is one, otherwise all are zeros. So such kind of representation is called the sparse representation. So this is also known as sparse representation of word vectors. So let's move on to our slides and see. Yeah, so that's how that was how one hot vector representation is drawn for a given piece of text in terms of one hot word representation. It has various limitations which does not allow to use for many complex examples. So first of all, there is no semantic information captured for each word representation in that, because each word is just opposite to another word. Okay, so how that we can understand it, if we just find out the similarity of two words, you will observe that first of all the cosine similarity is zero, means no word is at all similar to each other, even though there are two words which may have similar meaning, but one hot representation will not capture that. So that's why there is no semantic information. Even if you are going to calculate the Euclidean distance of two word vectors, you will always get the same value. So there is no at all any semantic information that you can use. And also it suffers with the curse of dimensionality issue, because if in the corpus there are large number of like thousands of words, so each word has to be represented that by that many dimensions, and all most of the numbers would be zero except the only one which is nothing but the index or id of that word. Otherwise most of the values would be zero. So yeah, for larger problems, it's not suitable. And the vector formed is very sparse, most of the value zero. So not a good idea to use it. And that's why more better word representation are suggested afterwards. We'll see that. Okay. Now, so that was example of non-semantic representation. Next, we move to understand some of the semantic word representation methods. And to understand what is a semantic word representation, there are some very good quotations given. So just we can get a lot of value by representing a word by means of its neighbors. Okay. Similarly, by J.R. Firth in 1957, he said that how a word can be defined. You shall know a word by the company it keeps. Okay, so this sentence tells that a word can be better identified by its neighboring words. Okay, if bank, there is a word bank in English, so it also used for this river side, and it also used for the financial banks that we go for opening account and all. So how to differentiate the use of two banked words? it actually the surrounding words. If the bank comes with some financial terms, so definitely you will understand that okay, this bank is something to do with the financial institutions. If the bank has surrounding words which represents the uh, some jungle or some riverside area, then you will definitely understand. Okay, it's talking about the river and its edge. So that's how the more semantic information a word carries, and if we are able to represent it, that will be the best representation for a given word. With this example, let's try to see. So, built in Belfast, Ireland, in the United Kingdom, the RMS Titanic was the second of the three Olympic class ocean liners. So, here, if we want to understand about the Titanic, each and every surrounding words plays a very significant role in understanding what Titanic is about. Okay, so where it was built and what it was, and it was built for oceans, something like that. So according to this distribution hypothesis, all these words play a role in representing the meaning of the word Titanic. So if any representation method followed this criteria and used the contextual or neighboring information and then represent the word, it will be more meaningful and useful for various applications. Okay, so we'll see some of the approaches which follows this criteria, and one is co-occurrence matrix, the very useful one. So it uses some neighboring information and represent the word. So it is actually a window-based matrix generation method, which captures not only syntactic information but also semantic information. The matrix is symmetric, means it will be n cross n matrix, where n is nothing but the size of the vocab or size of the unique words which are there in the corpus. Suppose our corpus consists of three sentences: I like deep learning, I like NLP, I enjoy flying. And if we construct the co-occurrence matrix, it would look like this. If any step you get doubt, just let me know. I will try to answer those doubts. So yes, so with that, these three sentences as an example, if we try to construct the co-occurrence matrix, it would look like this with window size 1. Window size 1 means only one neighboring word you are going to look in the sequence of words. So I like, it has value 2. So it means I like must be coming two times in this sentence. Yeah, I like and I like. So the pair of words comes to at two places in the corpus. I enjoy, it's only one. Okay. L- like I, yeah, because this is symmetric. So I like and like I both will have the same value. Like, if you observe, there is no two like together somewhere. Yeah, so that's why 0. And yeah, like also comes with deep and NLP. Yeah, like deep and like NLP. So there also we have one. So if you just follow this criteria according to the window size and fill this co-occurrence matrix, and you will get a vector for each word. So like for I, the vector is 0, 1, 1, 0, 0, 0. So it has more information as compared to one hot vector. Although the matrix is still sparse matrix, but it carries some information like what the surrounding words are there for a given word and based on the vector. If we increase the window size, maybe the co-occurrence matrix will have more information for a given word vector, and maybe it will be. So that's exploration that has to be explored explicitly to find out how this window size play important role in generating the word vector by this approach in a more effective way. So yeah, so better try to look with this with example on the collab to understand how the co-occurrence matrix is made, and the word representation is obtained. Okay. So for generating the co-occurrence matrix, we made this simple this simple code, and yeah, we need a Panda library, NumPy library, and this dictionary construction library. And what we need to do is uh, find out a corpus. So suppose we take this corpus an example, which consists of a few sentences. I like deep learning, I enjoy NLP, something. And yeah, so 1, 2, 3, 4, 5 sentences. And we give this corpus to this function co-occurrence. Okay, this co-occurrence function takes two variables. One is the corpus, another one is the window size. The window size help us find out the context, use the context to find out the neighboring words, and then generate the co-occurrence matrix. So don't worry, I will share this the collab links. You can play around and check what is happening inside that. So this co-occurrence matrix will loop over all these sentences in the corpus and process each word one by one. And for each word, it check the the next words as per the window size. Okay, window size is 3, so for each word it will check the next 3 words and try to uh, see for the pairs, count the pairs. Okay, and after counting the pairs, it will fill this dictionary value. Okay, so if any pair like I like comes at 3 sentences at 3 places, so ultimately the pair of I and like would be 3 after processing all the sentences. So when we have counting of all the pair of words, then we'll use the Panda library, which creates the data frame. Data frame, nothing but the tabular representation of the data. So it will create same co-occurrence matrix as we have seen here. Okay, so n cross n. So let's execute it and try to see how it is going to happen. So yeah, first line. Okay, then sending this corpus, and this will return a data frame. Okay, so data frame consists of word, cross word, and the value. Okay, how many times 2 words occurred in the entire corpus. And when you print the data frame, it will look like this. Yeah. So deep enjoy in the corpus. Deep only comes with thinking, learning, and yeah, because we have set the window size 3, so it will check with larger context window. Okay, so deep also comes with I. Okay, so yes, so if you take this much context, because 3 words can be together, I like deep, so I is also associated to deep. Okay, I also comes with deep because it is in the 3 context length window size. Okay, and deep also comes with is, yes, here. Deep also comes with learning, here. Deep also comes with meditation, here, because meditation and deep are 3 length closer to each other. Any words which is beyond the 3 length, it will not be paired up and it will be considered as 0. Okay, like I and eat. they are in the context of 4 window size, not 3 window size. So I eat, you will find out as 0. Okay. There must be somewhere else where because of it, it may be there. So this is how the this concurrence matrix will be filled out, and you will get the vector for each and every word, and which you can use for various applications like finding out the similarity of two words or finding out the similarity of two sentences. So this next example is just using the other way of generating the one-hot vector instead of using Keras, just using the TensorFlow. So it's the same example. Okay, so moving ahead, yeah, we have already seen that one. Semantic representation. Okay, now this co-occurrence matrix based word representation also has some issues. First of all, if the vocabulary size is very large, this matrix is going to be very sparse and most of the values would be 0. So although it has some useful information, but that sparsity issues is still there. For very high dimensional space, it required a lot of space, lot of storage space to save the co-occurrence matrix and use it for generating the word vectors. Yeah, that I wanted to talk about it. And next we need to find out some semantic word representation, no doubt, but in a more effective way, which can represent each word in a very low dimensional numbers and also carries most of the information into that. So what would be the other methods? Let's see them one by one. So this is the idea that we want to implement with expected word representation model, which takes suppose one hot vector at a time. Suppose cat.
Sir,
Yeah, yeah,
so just a small doubt. So
yeah,
in the
sure.
co-occurrence matrix, so when you say window size, so suppose if I say I like machine learning. So in this, if window size is 1, 2, or 3, so does it matter that if I say window size is 2, so I like machine learning. So in this, I will be counted as a 1, and then next two words will be there in the windows. Like, how does it start?
Yeah, definitely. You said the true. When you set the window size to, because you just have to work around this line. Okay. So if suppose the current word is I, so it will take up all this the coming words into the sequence. The coming words means I plus one to I plus one plus window size. Okay. So I with next two words, that's what the next words in that window size. So now you can predict like what would be the neighboring words for the I. If you are setting window size 2, you have to consider only the next two words, not beyond that.
Okay, so
Okay.
it means that we are taking into account the word itself and the two words after that, or one words after that, depending upon the size.
Depend, yeah, definitely. And same thing being done here as well. So here what is happening is the current word is taken into consideration as a token, and based on the window size, the next words, next set of tokens which are there in the sequence, and based on the window size, they will be considered as pairing up and counted as a co-occurred words. So that's how, yeah. Good doubt. That question need to be cleared. It's very important point for the co-occurrence matrix. I'm glad you asked. Okay, so the last two methods were both the sparse methods because they're based on sparse matrix generation. We need to find out some dense representation. So dense representation, how it is different from the sparse representation. Its objective is to represent a word with less number of dimensions. Okay, so earlier we used to represent a word with 1,000 number of dimensions, whether it is one hot vector or the co-occurrence matrix, uh, total number of words which are there in the corpus. Now we want to represent a word in a much smaller dimension space and with carrying all the useful information into it. So we need to think of a model which initially will be trained on the given corpus. So it will take one hot vector of a word, and then by some training method, the model is trained, and then when training is done during inference, any word we give it to give it to this model will generate a vector of length, suppose 100, 200, or 300 something. So that dense representation will be useful and effective for many applications coming ahead. So let's see what are some of the methods that we can try here for similar one. Yeah. So this is one example of word analogy that we can use word representation to solve some problems. Like when we you take the word vector of king, word vector of man, word vector of woman, and do this arithmetic operation, vector of king minus vector of man plus vector of woman. So whatever vector you will get, it will be very, very close to the vector of q. So it means if we find out the most valid semantic word representation and you apply this word analogy, that property would be carried in all those word embeddings, word representations. So we'll see with some examples at the end how this word analogy task could be implemented with the word representation in a more appropriate way. So this is the one of the very important characteristic of semantic word representation. So if two documents, although they don't carry any overlapping words, but if they are semantically close to each other, their semantic representation will also be closer. Okay, means suppose in document one, the words are Obama speaks to the media in Illinois. Okay, and another document, the president greets the press in the Chicago. Okay, so there is similarity word by word. Like Obama was a president, so both words will be closer. Speaks and greets are closer. They both are a way of our speaking. And Chicago, Illinois, they both are in USA. So kind of they both in one way they're similar to each other. Press and media also represent the same close information. So when we have more better semantic word representation, the two documents, although don't carry any overlapping words, when we multiply their representation, we will get more higher similarity score. Okay, so that's we need to understand, and we'll find out with examples in the coming exam slides. Okay, so to find out more appropriate methods, there are word-to-vec models available, skipgram model, and one more is there. We'll see after it. So the skipgram model is a criteria, is a model to train a model in such a way that it learns the representation of a word during training, and when the model is trained we extract the representation of word and use it for various inferencing tasks like machine translation, analogy, classification, or whatever you want to do. So how the training is done, which makes its strength in representing a word in a more appropriate way with more useful information. So we need to understand it. That's the important part here. So the main idea behind this implementing this model is, instead of capturing the co-occurrence that we saw in the last method, we predict the surrounding words for every word. So this is the objective here. So you will train the model with this task where the objective is to take a word and takes its surrounding word. Suppose two words previous and two words next. Okay. And then one by one predict each word. And if in predicting you get errors, you need to use that error to adjust the weights of the model. Okay, and ultimately when you train uh, on a very large corpus with very large number of epochs, the model weights are adjusted in such a way that it takes any word later post training and find out its representation in a more accurate way. So this is the training criteria, means predict the surrounding words for a given word and train the model. And during the inference time, during the testing time, predict. And also you can set the length of the window. Okay, you can choose the two words previous two words next, or only one word previous, or only one word next. So it's up to you. You can set the length of the window 5, 7, or whatever. uh, so the objective function here is to maximize the log probability of the context word. So suppose in a window of size m, you just take the center word out and try to predict each and every surrounding word, take the log probability, sum of them, and then use that error for adjusting the weights. Okay, so that's the criteria which are used for training a skip-gram model. So that's why its name suggests that skip-gram means it's kind of a gram-based method, 1 gram, 2 gram, by gram, or 3 gram, 4 gram, and we are skipping the center word and considering the neighboring word for predicting them, and based on this criteria train the model. So yeah, by this diagram we can better understand. So any WT, there is a projection layer, or we can also call it linear layer, uh, which is being trained uh, with the objective of predicting the next words. Don't think that all the surrounding words will be predicted together. The prediction will happen once at a time, like WT2 minus 2, and in the next iteration it will predict the WT minus 1. In the next iteration it will try to predict the WT plus 1. So that's how word by word prediction will happen. If there are any errors, that will be summed up, and at the end that error with some modifying with the loss function will be used for adjusting this projection layer. So ultimately this layer would be modified, okay, this projection, and it will, after training, this modified projection layer will help us getting the representation of a given word. Okay, so that when the model is trained, we got the embedding of a given word. We can use a linear layer for the classification into classes, or suppose here what is happening, it's predicting the next word, because that's the main objective of the language model. For the, suppose the word is yeah, so the word is dog. So what will be the next word in the sequence? So it will, the linear layer will take this word embedding and try to predict the next word. So you will observe that the bark will have the highest probability. So it means that after dog, this word should come in the sequence. Okay. Similarly, there is another method uh, uh, in place of skip-gram method, which is continuous bag of words model. So the criteria looks very similar, but slightly opposite to it. Like there we predict the surrounding words. Here we predict the central word. Okay, predict this current word. Current word nothing but the central word based on the context word around it. Okay, so better understand with the diagram. Yeah. So it takes one word, or we can say, yes, so this is nothing but the one hot vector of a particular word, and they try to predict the central word as a noun. Okay, so here also the hidden layer, which we call it the projection layer, will be trained with this criteria, and when the training is done, uh, it will be used for generating the word embedding. So with enough exploration and experiments, uh, people have found out that scriptgram is more useful, more better accuracy for various NLP tasks, but their performance are very, very close to each other, both continuous bag of words and the scriptgram model. Okay, so better take the example on the collab and try to understand how this the word to vec methods, whether it is skipgram uh, or the CBOW, is used to find out or train or use the uh, word representation of a given word. So without wasting time, let's go creating. Okay. So GemSim libraries is there, renowned library for training and using Word2Vec embeddings. So we'll directly use it and train and see how this will be useful for generating the word embedding. So yeah, the library is loaded. Here we have sentences. So if you want to train your own embedding, this the corpus you need to give as a list of words, not a sentence directly. Okay, so this is the first sentence for word to work. You this is one sentence, so you already have to split the sentence into words and then give your entire corpus to the word to work model for training. Okay, so how the word to work function will be used for training. So the word to wake, which we just got, will take the entire corpus. Okay, and minimum count means there is a threshold if you want only very high occurring words. Okay, so you can set it higher. So it will consider only those terms for which the count is above that decimal. If you set the minimum count as suppose 10, so it will consider only that word which comes at least 10 times in the corpus. And the vector size means what is the length of vector that you want at the end for each word vector. Okay, if you set it 300, so for each word it will generate the word vector of 300. SG is a parameter to set it. If you set SG as 1, so the word vec will consider the skipgram model for training the word embedding. If you set SG as 0, so it will use the other method, the CBOW, for training the word vec model. So when you execute it, it will take the entire corpus based on the passed parameters. It will train and return the model as a now. And we can use that model to do various tasks like find out total terms which are there in the vocab and also get vector for a particular word. Okay, and let's execute and find out what happens. Okay, so when we executed it, you will see that we got some vector as an output. Okay, so we have printed the model. So this is the model, just the definition of these. So vocab consists of 14 words. The size is 300 and some alpha parameter is there. And so those we have also printed the vocabulary. The vocabulary consists of these many words. Sentence so this is unique. So don't consider that it has all the words which are there. It consists of only the unique words. And then we also extract the word vector of this word. Okay, so we pass this word as input and get the vector of it. And because we set the 300 length for this word embedding, so you will observe that the length of this word vector for this keyword consists of 300 values. Okay, and yeah, this is how the word vector is being trained and used. And now we can use this word embedding for various tasks, whether do the analogy or find out the similar words or something like that. The best part is, let's also see the size of it. Okay, the size is 300. The best part is, for this model we can save it into a binary file. Okay, and later afterwards we can simply load this model and use it for generating word embedding for any word later. Okay, means you don't have to do the training again and again. You can train on a very large big corpus and save the model as a binary file and later use it for for your purpose, whatever you want. So this was a simple example of training your own word-to-vec model and use it for your purpose. Let's move ahead on the slides. The code is very simple. You can play around. I will share with you. Okay, that's done. And now see a demo and try to see how the word embedding could be useful for more practical examples. And yeah, by loading a standard word word embedding. Okay. Yeah, so yeah, I was executing. So I already loaded. It was very big, around 1.5 GB of this embedding. So I loaded it already. So we can play around with it on various tasks. So for each any word, the shape of the word vector is 300. We also set up a function which takes two vector and returns the cosine similarity. Okay, so this is the function of equation of cosine similarity, which performs the dot product and the divide with the normalized the multiplication of their normalized representation. And yeah, so if you just get the vector of cat, get the vector of dog, and find out the cosine similarity, you will get this value 0.76, which says that the cat and dog keyword are used in the corpus more interchange way. So they have some similarity, kind of animals and occur text more closer to each other. And suppose you want to get top 10 words which are very closer to cat. Okay, so you can use this function similar by vector. So okay, so this function will return top n words which are similar to cat. So let's execute it again. So first of all, the cat is there by itself. The probability is 1. Cats is another word. The probability is also very high, 0.8. Dog, 0.7. Kitten is also very closer. Felon, beagle, puppy. So these all words which are very, very closer to cat. So by using the word-to-vec library, you you can obtain it. Now the example that we seen in the slide of implementing the analogy. Okay. So if we estimate this vector, okay, find the vector of actor, vector of man, vector of women, and do this arithmetic operation. And whatever the vector you get, just find out the top 10 vectors similar to that. So you will observe that the actress, okay, is the first very close words which is written as a noun. Okay, so actor with this analogy, actress is the most closest one. Now, as in the slide, the example was king minus man plus woman, and the output should be queen. And let's see if it returns the same. King, queen. Yeah, it returns king as a most relevant word to this vector. Yeah, the queen is also there, the next to that one. So that's how you can play around and see, do some analogy. And if you want to represent a sentence like Obama speaks the media in Delhi, so it will return, you just find out the vector of each word and do sum up. So it's kind of a representation of entire sentence. So vector 1 represent the word to vec for entire sentence. Vector 2 represents the word to vector for sentence the president greets the press in India. Okay. And the third sentence is the representation of sentence is the dog chased the cat. Okay. And if you just find out these word vectors and find out the cosine similarity, you will observe that it carries some useful information. So the obviously the vector 1 and vector 2 should be closer, and if you find out the cosine similarity, sorry, they need to be executed first. Yeah, this one too, and then find out the cosine similarity. Yeah, so you will observe 0.65. It's quite higher. Okay, so it means both the vector, the first two vectors are closer. They are in some way similar, carry same information. But when we find out the cosine similarity between vector 1 and 3, you will get very low probability. That's the usability of semantic representation. When you have semantic dense representation of a word and use that word embedding to find out the representation of sentence, you can find out the how two pieces of text are closer to each other. So the vector 1 and vector 3, they are very like distinct to each other. There is no similarity, so the probability, the cosine similarity was also less. Okay, so the further examples are just how we can represent the vocab of a given word to vec model in a 2D space. So it's just a scale-learn method. You can try on your own to find out. So there are very, very large thousands of words in the vocabulary of a word. So that's why the image is completely dark. They all are words. And so you can play around. So this is how the word to vec models are trained and used for various different tasks to find out similarities or closeness of two pieces of text. So yeah, coming back to our slides. So that was the
Sir,
demo. Yeah. Please go ahead.
uh, can you go back to that collab file?
Yeah, sure. Yeah, let me know.
So where you have loaded that file, that data file, I think 1 GB or something you said.
Yeah, actually, it is already a GenSim word-to-vec model, and it is loaded by this library, and it is already there on the cloud. Okay, so the word-to-vec Google News. So it is trained by Google on some news corpus with 300 word-to-vec length.
So does it mean that this file contains basically vectors created from the news items?
Yeah, definitely, yes. So, yeah,
Okay.
there are also very
And
bigger models available, like large GB models. So they will have more better information, more better representation of words that we can use. But the overall idea is same.
okay. And so to the later part of this, I have one
Yeah,
more
yeah,
question.
yeah. Here somewhere.
Yeah, where you were showing similarities
Okay,
between two,
similarity
I think
of
in chapter
words.
one. Yeah, this,
Yeah.
yeah, this was a sentencer.
Hmm.
Because some people are from linguistic background, so maybe if I'm wrong, I don't know. I just have a very basic doubt over here.
Yeah.
So you talked about all of them as a vectors which are taking care of semantic similarities, right?
Yes. Mhm.
So if I have a sentence, Obama is the president,
Okay.
and Obama is not the president,
Okay.
and
Then.
cat is
Hmm.
the animal. Okay.
Yeah.
So my hunch is that Obama is the president and Obama is not the president are totally
Hmm.
semantically opposite things.
Yeah. Yeah.
But by
Definitely.
this
Yeah.
logic, it will show that these two sentences are semantically similar.
Yeah, it will show because I can tell you one thing here is because they are individually word representation. And when you use this word representation to find out the representation of a sequence of words, so it carries some semantic information, but due to the syntactic similarity, because there are a lot of words which are common between the two examples that you mentioned. The only difference is not keyword, and so that's why the future techniques, the LSTM model, the RNN model, which dynamically takes the entire sentence as an input and generate the representation, that will have more better quality of sentence representation. Just by using the word representation and use that word vector to represent the entire sentence will not carry the entire information, and may or for sure is going to fail, as you just mentioned with your example. So that's why the language modeling approaches, which takes the entire sequence as input and then generate the sequence representation, that will carry the more useful information, and will also take the example of the semantic and syntactic information, and you then you will get your expected output in that scenario. So it
Understood.
was very clear. Yeah, very good question. Definitely. So it requires more advanced examples. Not so advanced, only the methods that take the entire sequence of words, or we can say sentence or paragraph, and then generate its representation. Here, what we are doing is just summing of the vectors, and considering it carries all the information, because it does not actually, and may lose some information during this arithmetic problem. But the idea I wanted to let you know is that these word representation, they do carry information, but it up to us how we can use this representation with some projection and recurrence layers to solve the complex problems. And with future tutorials, we will try to understand. We are just building up the background with this the basic examples to have some building blocks and use it for future explorations and problems. Okay, please let me know if anyone else has any other doubt. We'll talk about it, and you can also play around with all these collabs. We are going to share with you, and you may get some library issues because for some of the examples, because Gensim has updated recently, so you have to find out like some compatibility with older Gensim library and the newer Gensim library cases, but that's a trivial case here. Okay, so let's move ahead, so that the examples we already saw. Yeah, that's it for today. Okay. So thank you guys, and if you have any doubt, you can already write to us. And the next would be to share the slide with you, and also explain what you have to do and what will be the task that you have to complete and submit before the next day starts. And yeah, happy learning. And if you have any doubt, just let me know. We'll be here till next like more half an hour more. So probably there will be a quick break, and then I will join back. And please be in the meeting room. We'll be sharing and discussing the assignments. Okay.
Okay, hello, am I audible? Hello.
Yeah, yes, audible, yes.
Okay, I'm audible, right? So I'll be now presenting the assignment one for this particular Jan course. Right. So this is the assignment that you will be given. Right. So in this assignment, you will be given one code file, uh, which has a particular set of code that is used to generate word embeddings from a piece of text. Right. You have one other helper Python code file, which has a bunch of questions that are used to generate some particular uh, parts of the code. They may or may not be useful for particular your implementation, right? And the assignment also includes a huge chunk of text, right? So in order to create word embeddings, we need a lot of text to learn from, right? So this is the text that you'll be using. It's the sonnets by William Shakespeare and the entire text of it, right? So this is the text. Oh, sorry, this is the code that you are given. Just move this way, right? So what is the goal of this assignment? In this assignment, right, you have till the end of the day to finish some filling the blank statements in the code. Right. In the code, there are five sections that are missing one or two lines of codes. Right. And then you have to, based on the formulas that are defined, fill in those code blocks. Right. The exact thing that you have to do would already be defined in the text above. All you have to do is convert that particular textual information into code. Okay, that's the thing that you have to do. So you have to study the notebook that is provided in the assignment. There are five sections of the code in the file that are missing the code, and you have to search. You can also search for these missing code pieces by using the term start code here, right? And then each section holds 2 marks, so the entire assignments hold a total of 10 marks. And the assignment is to fill in the missing code to ensure the output corresponds to the expected output after each exercise. Right. So for example, if you look at the code, uh, let's say this is the exercise. After each exercise, you have been given expected output. So when you fill in the blanks, so for example, when you fill what is W1, W2, B1, and B2 should be, and after running the code or these cells, your output should match the output given after each exercise. Okay, I hope that part is clear. What you have to do. Now we will be going over the entire structure of the assignment. And if you have any questions aside from the actual code that you have to write, you can ask. Okay. So this is the general idea of the assignment. We are supposed to practice how to compute word embedding, and we'll be using them for sentiment analysis. The actual analysis part may or may not be included in the assignment, but your particular goal would be to visualize these embeddings that you have trained yourself. Right. In this assignment, we'll be using the continuous bag of words model. Right. So the idea of continuous bag of words has been explained, I believe, before. The idea is that you have a word and you will take words in the corresponding window across that word. Right. So for example, we have this sentence, I am happy because I am learning. Let's say we want to learn the embeddings of the word happy. Right. So for the word happy, so target equal to happy, the context is I am because I. Right. Two words behind, two words ahead. We are taking a context window size of 2. Right. So in this way, we are trying to define the window. So how do we calculate these word embeddings? First, we calculate a dense representation based on some W1 on D1 weights. Right. Then we calculate some non-linearity. Here we are using the ReLU function. Right. The exact function is not really that important to you because this function is already defined. Right. The actual thing that you have to fill is how to define these H and Z. Right. And the functions that you have to use are also defined in the actual text as well. Right. So from those who might be aware, I think Sir mentioned in his assignment that this is how perceptrons are written. Right. So weight x plus b is equal to the layer. Right. So perceptron is equal to ax plus b, something like that. Right. So this is how our this particular implementation also handles these neural networks, right? So first layer, then an activation, then second layer, and the final layer is softmax. The softmax is also defined. For example, if you go to the bottom, you can see that softmax is defined using this function exponential to the power zi. Zi is the element that we want to calculate the softmax for, divided by summation of all the elements, all the j that are present, right? So one element divided by the summation of all the elements. All these elements are exponentiated. So all you have to do is convert this particular formula into a Python representation of that particular formula, right? So it would be something like np dot exponential, and then you will use your own way, right? So the idea is that you have all of these information already provided to you. All you have to do is convert this information into Python code. For the implementation of this assignment, you are not using any high-level library. All the libraries that you will be using are NumPy, the utils package that also contains predefined functions, and these predefined functions also only uses SciPy and NumPy library, right? So all of these are basics library. Keras, PyTorch, all of these advanced functions you will not be using, right? You are working with basic Python and some basic machine learning level Python, right? So starting from the first section, you are importing all the required packages, right? You write NLTK data.part.append, so you download the sentence tokenizer. If you do NLTK.download, right, you can download all the functions that are available in NLTK, right? If you are interested in trying all of them out. However, for our use cases, we will only be using the sentence tokenizer, right? The second part of the code opens the Shakespeare.txt file. So this is how you open a file in Python. Open Shakespeare.txt and you use the with keyword to make sure that the file closes itself automatically. Right. So data is equal to f.read. This is another Python syntax, how to read a file. Right. So now data holds all the text that is in the Shakespeare.txt file. Right. We apply some regular expressions to remove punctuations or replace all the punctuations with full stops. Then we tokenize all the words, whichever tokenizer we are using. Here we are using sentence tokenizer, right? Data is equal to ch.lower, and as mentioned previous time, like in yesterday's session, the last step of pre-processing is lowercasing all the text, right? So you remove all the uppercase words, you tokenize, and you also remove all the punctuations. This is how we are pre-processing our text, right? And then we create the vocabulary, and if you, let's say, run all of these commands, right, you will see that our Shakespeare.txt file has a total of 19,808 tokens, and some of the tokens are the sonnets by William Shakespeare, from Paris, Creatures, and so on, right? So all of these are tokens that are available in the Shakespeare.txt file, right? And then when we try to remove all the low frequency words. So I think yesterday we did that. All the words that had a very low amount of frequency, we removed them, right? So we are doing something similar here as well. All the words that have, let's say, less than 20 occurrences, we are removing them, right? So in order to make sure that our codes run faster, right? After doing this, we have a total vocabulary size of 3002, and these are the most frequent tokens. Full stop occurs 2413 times, and occurs 490 times, the occurs 432 times, to occurs 408 times, and so on. Right, so this is our vocabulary, and then what we'll do, we will map these particular vocabulary to some index. Right, so basically we want a numerical representation for a word, and we have not yet gone to the stage where we have defined our word embeddings. So to have an intermediary representation of each word, we have created an index for each of the token, right? So for example, that when we do our index to word dictionary, let's say king has a representation of 1405, right? And the word with the 2734th index is upward, right? We can also check out the entire thing. So word to index is our library. We can just do word to index, see what it is. So it is our Python dictionary, which holds all the vocabulary that we have, right? All the words that are in our Shakespeare.txt file with a count greater than 20, right? So full stop is at the 0th position on our dictionary. Is the second word. Abhor is the third word. Abide is the fourth word, and so on, right? So all of these are indexed. And then finally, we have a total of 3002 words, right? So this is all the pre-processing that we have done. That was also mentioned yesterday. We remove the punctuations, we reduce all the text to lowercase, and then finally we tokenize as well. And then after this, what we'll do, we'll train our model, right? And we'll training our model based on the tokenization. And then after this, we have our exercise. So first step of the exercise is to initialize the weights and biases that we'll be working with, right? So we have already defined W and B that they should follow this particular format. I'm sure you're aware of in equation of a line what W and B should specify, right? So in the similar way, you have to write the definition of W and B here, right? The shapes are already given, and you can read this particular text to this figure out what the initial values should be. And then you have to check for the values, and these should be the final values that you get. Right, the second problem is to implement the softmax function. This is the softmax function that you have to implement. Here, in the second section of the code that is missing, you have to write one line which converts this particular function into a Python code. Right, and this is the output that is expected after you fill your code correctly. For the third exercise, you have to implement forward propagation. So what is the idea of forward propagation? You take the values and you move them forward to generate some final embedding, right? And in this particular function, you have all of these h, a, z, and f of h that you have to apply and fill, right? So first example, h would be equal to wx plus b. So you will check how you have represented w, x, and b in the codes above this section, and then replace them and fill them here. This particular section would apply the value activation function to the previous value of h. This z calculates the value of z based on this particular function 3, right? Sorry, equation 3. And then finally, you just return z and h, right? And then when you fill these particular values and apply the correct values, you will get this result, right? So your particular output for this particular above cell should match this particular expected output, right? And then this particular section has no fill in the blanks for you to match, right? If all three of the above things are done correctly, this particular output should match by itself. In exercise 4, you have to implement the backpropagation part. Of course, the backpropagation part is gradient descent, right? So the gradient descent part would be alpha times whatever your gradient value is. The gradient values are already calculated. You have to calculate the gradient value for the W2, right? So W1 I have already calculated. You have to calculate the gradient value for W2. Similarly, gradient value for B1 I have calculated. You have to calculate gradient value for B2, right? And then finally, again, if you run the code correctly, implement the code correctly, it should match the output given here. Finally, for the fifth problem, what you have to do is you have to fill the values of this W2 and B2, right? W2 and B1, W1 and B1, W1 and B1 have already been filled by me, right? You have to fill these two missing values, which are W2 and B2, right? Of course, these values should be upgraded based on the gradient, just how W1 is updated. Similarly, W2 should also be updated, right? I hope all of these parts are clear. After each step, you have to match the output, and the output should match in such a way that the corresponding output of your cell should match the expected output, right? And once you run your final code, all in all, you should get something like this when you run the last cells, right? You will get a new representation in the vector space for each and every word. Now these representation are not very good because we have only done a few instances of training, right? Generally, we will require a lot more data and a lot more time to run our code for multiple instances, and then we will be getting good embeddings. But as you can see, even by running it once a second, we are getting some representation, right? So, for example, if you see something like okay, here I guess nothing really comes very well. But if you run it multiple times, you would get a better representation of the tokens, right? So similar, what you're trying to see is that maybe king and man will move closer. Maybe like man and woman have the same direction as king and queen. Right? Something like these should show up after you run your code multiple times. But that is out of scope for your current implementation because we do not expect you have to the resources to actually run this in that particular part of the assignment. Right. So for this particular assignment, all you have to do is look at the sections of the code that are missing. You can search for these sections by searching the term start code here, and in that code there are values that are missing which have been marked with none, right? And you have to fill these none values. Okay. I hope that part is clear. If you have any questions, please ask. Okay, if there are no more questions, I'll be sharing the assignment with all of you. Right.
Sir, are there any installations required for running these files?
The installation would correspond to directly the let's say here, right? So all the functions that are here, you have to install. You have to install NLTK. Maybe what I'll do, I'll write a line here. In the first part of the code, I'll write everything here. If you use Colab, most of these things should already be installed, but you can install it using pip install. You will require Stacy, right? Other Stacy, you will require NumPy, right? Other than NumPy, you require NLTK, right? And let's check the utils file. If utils file says pipe. Uh, right. So all of these things you are required, and what I'll do is after that you will run NLTK download, and this should take care of all the installations that are required. Okay. And as you can see, output created, so it's just installing. This part should okay. I'm just adding a queue as well so that it doesn't give you a huge pop-up. Right. And then you can run nltk.download to basically uh, install all the required packages. So I hope that part is clear. All of these two lines that I've added should install all the packages that are required. Okay. So this kind of this is what you call it. Pop-up will come up, right? And it will show all the packages that you have to install, right? When you click on download, it will install all the packages that are missing and you are required to install. Right, after you are done with it, you can just cut it and it will install all the packages. Right. I hope that is clear. Any other questions?